Wishbone, and this is Hard Rock University. Today I'm trying a little bit of a different format where hopefully I can use this area up here as kind of a virtual whiteboard for graphics. I'm just kind of testing it and see how it works out. Now, when I was up in Montana, the viewer was most uncooperative, and so I've kind of embarked on a new series of tests. Among other things, I need to educate myself a little better in the precise fluid dynamics and physics of the settling and such of the particles. And as part of that, I got a couple of aids here. Number one, this is magnetite. It's a fine powder, supposedly 500 mesh. I checked it out. It varies quite a bit. But this is a good simulation of both natural magnetite powder, or if you had a similar material like sulfides in terms of density. So this gives me something I can play around with in sufficient quantity. I can really see what's going on, and I can do just this, or I can mix it with other materials to see what happens and have better control. Another thing is tungsten powder. Now, tungsten is one of the very, very few materials out there that is as dense as gold. Pretty close. This is about a density of 19. Gold's about a density of 19. There are other materials that are of similar density. I know that platinum, palladium, iridium, osmium are all about in that range. The problem is they're all quite expensive. This, on the other hand, half a pound for it's about 30 bucks delivered. In smaller quantities, you can get they use this for weighting golf clubs. You pull off the end, you pour it down the shaft, and get more weight. So if you wanted just a small quantity, you might try a local golf shop. But it's reasonably priced on the internet, and it's a little bit more consistent. Doesn't have as many big particles in it, but they say 30 to 50 microns. I'll go with that, although there's some bigger and some smaller. So I've done a couple experiments, and let me show you what I've done so far and what that shows us about these powders. And this is magnetite, black natural iron oxide Fe3O4, and about a half a spoonful in there. I've got that scale marked off in inches, and take it right up to the top there. Now I'm just gonna shake this like this. This is untreated tap water. And backlight it so we can see and start a split. So as you can see, it's settling pretty darn fast. Now this is your typical black sand. It's got about the same density as pyrites. According to the manufacturer, that's 500 mesh. According to my observations, it fluctuates a lot. The smallest particles are about 1/3 of a thousandth of an inch, or roughly 10 microns. And as you can see, it's only been 40 seconds, and it's already mostly settled to the bottom, and that's 4 inches. So call it 1 inch every 10 seconds. But you'll also notice some of it is floaty at the top here. Okay, so your natural reaction to that would be some jet dry. Put a little jet dry in there.
And now we still have a fair amount that's still floating there. So I don't know what it is. Maybe there's a little bit of oil still coating it from a manufacturing process or something. I don't know. But let's see what happens here. Okay. So now, stop, reset, start. We're seeing roughly similar results in terms of settling, apparently. But here's where it gets a little bit different. In 40 seconds, you notice it's not quite as clear as it was the last time. And it will continue to stay that way. So let me turn off the camcorder for a little bit here. Okay, that's 60 seconds. And I'll get back to it. So here we are, 5.5 minutes in, and you'll notice there's still a lot suspended now. Not as much on the surface, that's for sure. But we now have what appears to be some sort of particles that are being suspended by the jet dry. So whether it floats or stays suspended, either way you're not going to be able to recover it. So that's not necessarily a good thing. We're not getting clarification of the water. Okay, now here I have tungsten powder, and tungsten is one of the very few things that approximates the density of gold. It's very, very similar. This is supposedly 30 to 50 micron. And let's go ahead and see what happens here. Looks to me like there's the top of the particles, basically. And again, after about 40 seconds, they've pretty well settled. So there's not a great deal of difference in settling velocity there, it doesn't appear. Interesting. Interestingly enough, there's almost nothing floating on this, like there was with the iron oxide. Put a little bit of jet dry in here. And try that again. Oh, come on, stop. Well, actually, this doesn't seem to make much difference. You can see there are some particles there that are substantially finer. Now let's do some panning experiments. Well, this is tungsten here, and it should behave very similar to gold, and this is exactly what I see with the gold also. The very fine stuff, I mean, it just sticks to the pan. And tilting that, and it just sits there. You have to rinse it. And I can see more texture here than there. I don't know if the camera can, I kind of doubt it. But that's quite the lump. This is all that stuff that was in the little jar. Now this, I mixed it all together, panned this out of it, and then I have this material. This was just from the concentrator stuff that I'd panned out and was thrown back in to reprocess. One thing I found too is when you're doing this part of the operation, you can see there's a little bit of the black hematite there. That's a nice thing about knowing exactly what's in it. And you can't really see much in the way of tungsten there, but it's there. Now, if you take this, you can see there's coarser particles there. If you take this and rotate it as you're shaking, you'll see a tail of tungsten start to appear. That would also work with gold. And then go like this. Your coarser material is over here. And therefore, you put the 12 there, tilt it a little bit that way and this way. And see how the coarser material just launches right away? And there, hopefully I'm getting it in the screen. Here's your tungsten, or what would be the gold line. This would be your heavies, because that's what it is, it's iron oxide. And then here's your lighter, coarser material down here. And like that. So that's how it's easiest to separate that. I've found out that when I'm doing panning of ore and such, that same technique seems to work very well for recovering small quantities of gold. Again, once you get it all in a pile, then rotate the pan a little. And you can see any gold's already going to be in this area here. If it's a few particles, you may not see it. But that allows you to get rid of your coarser particles without losing the gold. You can even rotate it back a little bit. But you see how it tends to bring these right up in here? See how it tends to bring these right up in here, which is undesirable? Now that would be multi-ounce to the ton material. I'm gonna save that tungsten for other experiments. The other nice thing is with the iron oxide, It's real easy to separate it because all you have to do is use a magnet. I'm getting a more powerful magnet to do a few other little experiments with too. But there you go. The tungsten is a good proxy for gold. It's relatively cheap, half a pound for 30 bucks. And you can really play some games with it and have some fun. The iron oxide also allows you to have a reliable proxy for pyrites, things like that, without actually having to have them in the rock.
So there's our results. The settling was surprisingly similar to me. I thought the tungsten would settle several times faster than the iron oxide, and it was actually fairly similar in my opinion. The difference was the iron oxide, some of the smaller particles stayed suspended better when you had the jet dry in there. It kind of encouraged me to believe there's some surface chemistry effects going on here that are important when you start getting down to the really fine sizes. This also is indicated in the panning test. When you're tapping and tilting the pan, the larger particles of gold will tend to just slide down the pan, while the very finer stuff stays up at the top. And to me that indicates, again, it's a surface attraction sort of situation. This is not the same as a gravity separation. And I'm going to be doing some more experiments on that too to see if I can use that or a similar effect to recover the really fine particles of gold. And aside from that, the tungsten behaved very similar to gold in the pan. As a matter of fact, I got a little cross-contamination with some stuff I was running on tests, and the tungsten actually wound up a little higher in the pan than the gold. So that was interesting. But they do seem to be good proxies, and I will be using them in some other tests in the not too distant future to try and see if I can more precisely define certain parameters that I think are important to what we're doing here. But as some of you pointed out, there comes a point where you simply can't gravity extract, where you start getting into chemical extractions. I just want to make that as small as possible and as easy as possible, so that whatever you can get gravity or whatever you can concentrate and then tank leach, you can do that to improve the economics. So that's where we're at right now. Happy prospecting and keep it safe out there.